This video accompanies our 2022 CCP4 study weekend paper and demonstrates how we can use a molecular replacement solution found using pieces of an AlphaFold model to quickly fit the complete model to the experimental data in ISOLDE. In ideal cases, this approach allows us to skip the time-consuming step of tracing chains ab initio and focus on polishing the near-complete model. I have open an ISOLDE session containing 3 models. In tan, we have the molecular replacement solution from Phaser, based on 2 fragments obtained using Phenix.process predicted model. In purple, we have the AlphaFold model, trimmed to the experimental construct and with PLDDT values converted to B factors. This has been initialized for ISOLDE with the MTZ file produced by Phaser. Finally, we have the original AlphaFold model, which will be used to generate confidence-weighted reference restraints. This demonstration was recorded in a pre-release version of ISOLDE, in which reference restraints could only be added via the command line, which is what I am doing now. From ISOLDE 1.4 onwards, it will be possible to add and remove these via the graphical interface. First, we introduce a network of fuzzy interatomic distance restraints with strength and fuzziness dictated by the predicted aligned error between the atom's residues. Atoms more than 8 angstroms apart in the reference model, or with predicted aligned error larger than 4 angstroms, will not be restrained. Here I have also specified the display threshold argument, so only strained restraints will be displayed. In a similar manner, we then add restraints to all phi, psi, and chi torsions in the model, with strength and fuzziness in this case dictated by the PLDDT values for each residue. Residues with PLDDT less than 50 will not be restrained. When opening an MTZ file containing experimental structure factors, ISOLDE automatically creates a set of live maps which update as the model changes. This set includes a special map used as a fitting potential, but in this case, given the large deviation of the model, the maps generated by ISOLDE are not yet reliable. Therefore, we disabled the live fitting potential for the time being and hide the live maps. Instead, we will start by fitting to the pre-calculated map generated by Phaser. With the model restrained and the fitting potential chosen, we can now start a simulation to perform the initial bulk fitting. While in principle the MR solution could be used as a target to automatically fit the working model, in practice it is quite straightforward to interactively tug the misfitted domains into place using ISOLDE's tug selection tool. When performing this sort of large-scale rearrangement, it is also often helpful to reduce the view to a C-alpha trace by hiding all but the C-alpha atoms. Here the C-terminal domain is already well fitted, but the N-terminus is way out, so we select the first few hundred residues to tug into place. Notice that rather than pulling continuously, I tug in short bursts, allowing the model a chance to settle locally in between. Once the model atoms come within the radius of convergence of the target density, they settle obviously into concordance with the MR solution. At this point, we can stop the current running simulation. You may not have noticed the running R factor display in the bottom right corner of the window, but in the course of this initial fitting it has dropped from about 57 to 41%. That's good enough that we can now switch to using ISOLDE's live maps for fitting from now on. From here, we need to carefully inspect and correct the regions where the AlphaFold model conformation disagrees with the experimental density. Some of these disagreements are likely artifacts due to crystal packing, but it is important to remember that while AlphaFold models are often very, very good, they are not perfect, and even high-confidence sites can contain local errors. Here, for example, AlphaFold has clearly chosen the wrong packing for the side chains of this tryptophan and leucine residue, which may be the reason that the adjacent loop also deviates severely from the experimental conformation. This can be readily corrected by starting a local simulation, selectively releasing the reference restraints on the offending residues, and rebuilding. Like with the addition of the restraints, in the version of ISOLDE used for this demo, releasing restraints was only available via commands. Here I'm using the 2-character convenience aliases activated by first using the ISOLDE shorthand command. In the release version of ISOLDE 1.4, these actions are available via buttons on the Restraints tab of the ISOLDE GUI. While watching the rebuilding here, Notice how the combination of real-time model geometry validation with live map updates helps to confidently find the correct solution. Nevertheless, this can often involve testing a few alternative hypotheses along the way. Don't be afraid to do this. If you get hopelessly lost, you can use the checkpoint buttons at top left of the ISOLDE ribbon menu to revert to the starting state of the simulation and try again. This example highlights the important message that while this approach can help you quickly get started with modeling after molecular replacement, it remains critical to carefully manually check and correct your model against the map prior to refinement and deposition. In this case, completion of the modeling took a further 3 to 4 hours, first continuing this session to correct various gross disagreements, including symmetry clashes and one very mobile loop, followed by a round of refinement in Phenix.refine, and then a complete end-to-end pass through the model without AlphaFold restraints, checking and where necessary correcting the details of each residue.